before I start chapter 12, I will link everything from chapter 12 to chapter 11. And because I will link everything from chapter 12 to chapter 11, I will give you a review of what we actually did in chapter 11 and how we are going to do exactly the same in chapter 12. Yes. The thing is, for chapter 12, you need to recall two things. Number one, you need to recall chapter 11 of this course. And number two, you need to recall the multiple linear regression that you took in ISE 291. Now, if you recall the two of them, you will be able to understand chapter 12 in more depth. So let me first, before I go into the slides, let me first make a map for you where I will keep chapter 11 on one side and then I will make a similar map of chapter 12 for you, which is on the other side. You'll be able to link the two of them. So you started chapter 11 by defining a simple linear regression model. This is the simple linear regression model that you define in chapter 11, correct? From this model, what did you do? First step was to do what? You used an estimation method and you got the estimates for beta naught and beta 1. That was the first thing you did, correct? What was the second thing you did? You went from point estimation to interval estimation or hypothesis testing. The general formula for hypothesis testing was beta hat j minus beta j naught over standard error of beta j hat, where j was either 0 or 1. You did it for beta naught and you did it for beta 1, correct? Correct? And using the same t statistic, you also developed the confidence intervals, right? But when you did that, you faced a problem that in this standard error expression, there was sigma square, correct? There was sigma square. How did you estimate that sigma square? It was mean square error, correct? Which was sum of squares of errors divided by n minus 2. You also define an easier way of getting the SSE. What was the easier way of the difficult way of getting SSE is this summation EI square over N. No. Summation EI square. Where EI is YI minus YI hat. Where YI hat is beta naught hat plus beta 1 hat XI, the fitted values. Correct? Correct. Then you also designed a test for testing the significance of whole model. Let me merge this one in here. Okay, let me write it here. Test for testing the significance of whole regression. It was an F test, if you remember. It was SSR divided by 1 over SS E over n minus 2. Right? After doing all the tests, then you started using the regression. You use the regression for what two purposes? You used it for mu of y given x naught, and you used it for y naught, single value and mean value. For this one, you called it confidence interval or mean response. For this one, you call it prediction interval for single value, right? Somewhere at the end, you also defined a measure R square. That tells you how good is the regression. This R square stays between 0 and 1. Higher value means more variation in Y is explained by your regression. Correct? There was a whole chapter 11. Take your time and again review what we did in chapter 11. We started with defining the simple linear regression model. We said in this model, apparently there are two unknown quantities. We estimated those two unknown quantities using the least square estimation. We gave them notation beta naught hat and beta 1 hat. We called them point estimates of beta naught and beta 1 respectively. Then to move towards the interval estimation or hypothesis testing, you define the t statistics. Within these t statistics, there was unknown sigma. You estimated that using MSE. There was a longer way of getting MSE and there was a shorter way of getting MSE. The longer way is to get the residuals, square them, and all that. And the shorter way was to find SST minus SSR, the shorter way of getting SSE. Then you also defined a test of testing the significance of the whole regression. Again, for simple linear regression, you have only one regressor or one predictor or one feature. The whole regression is that one feature. So the t-test and the f-test, they were equivalent. They were the same things. Even in the t-test, you were testing beta 1 equals 0 versus beta 1 not equal to 0. You tested it using T and you also tested it using F. Both of them were testing the same things. Both of them were testing the same thing, but with different mechanism. But they were the same things, that beta 1 is 0. The slope is 0, because if the slope is 0, the regression is insignificant. You can test in simple linear regression, you can test it using T or F both. And also there was a relationship in this case that T square was F. This is only true for chapter 11. Then you went on to use the regression. You said the regression can be used for two purposes. Number one, it can be used to estimate the mean of Y for a given level of X, or it can be used to predict a single value of Y for a given level of X. And you said that the point estimates for both of them are same, but the interval estimates are different. You called one of them to be the confidence interval and you called the other one to be the prediction interval. The interval for the single value, you called it prediction interval, and the interval for the average value, you called it confidence interval. Somebody can close this door. Now, let's get to the problems of simple linear regression model. Now, in real life, if you have a response variable y, let's take an example that response variable y is your score in major 2. and X was the study hours, let's say. How many hours you study, and your score is Y. Do you think that the score in major only depends upon the study hours, or it depends upon many other factors? Many other factors. In real life, in any regression example, if you have a response variable Y, do you think that Y depends upon only one feature or one predictor or one regressor, or it depends upon many regressors? Your monthly expenditures, do they depend upon only income or do other factors? Other factors, how big is your family? Where do you live? How much do you travel every day? What is your standard of living? What is the cost of electricity? And so on. It depends upon many other factors, right? So in simple linear regression, we are actually ignoring all of those factors, and all of those factors were going into what? They were going to the error. More you ignore, higher will be the error. Now, when you said in chapter 11 that the score in major 2 is dependent upon study hours, there are many other factors which are affecting your score. All of them were going to the error. Because you did not accommodate them into the regression model, they went into error. So in a sense, error is actually what? Error is all the predictors that you ignore. It's all the random variation that you cannot capture. Of course, you cannot capture everything. So whatever you cannot capture goes to the error. But chapter 12 says that at least you should make an attempt to capture as much as you can. So what we do in chapter 12 is we bring all the factors that we think can affect Y. So we define a multiple linear regression model, which is the generalized form of this one. Chapter 11 becomes a special case of chapter 12 now. I will use the green color for this one. And I will map one to one. Everything I will map one to one. We will repeat the whole thing without any change. The first thing we will do in chapter 12 is we will define this model. Now the question is, let's say you try to identify that your major 2 score is impacted by 1. What do you think? What is your major 2 score impacted by? Study hours? Let's call it X1. Let's say your IQ, X2. Environment, X3. Hours registered, X4. Sleep, X5. Anything else you can think of? Whatever. Do you think that whatever factors you told me, these are the only ones affecting your score, or still there are more that you cannot even imagine? So still there are more which you cannot accommodate all of them. Still you will see the error term, epsilon. So whatever you are able to identify, they will be X's. Whatever you are unable to identify, again, it will go to the error. So this is called, on the left side in blue color, is called a simple linear regression model. On the right side is called multiple linear regression model. And in this multiple linear regression model, if K is 1, you go back to simple. K is the number of features. Some books call it regressors, some books call it predictors, machine learning terminology call it features. What will be the first step? To estimate these quantities. So the first step will be to estimate beta naught hat, beta 1 hat, beta 2 hat, all the way up to beta k hat. Now the good thing here is, in ISE 291, do you remember how did you estimate these quantities? But what did you code? You wrote down this model in the matrix notation, and then you estimated the model in the matrix notation, X transpose X whole inverse. I don't know if you remember it or not, but this was the formula you used. Do you remember or not? You took it or not? It should be taken by now. It should be done by now. It is in which chapter? 7. And you should be done with chapter 7, is it? Or you're doing it now? I took a quiz. On this one? This was the formula. But the good thing is that in this course, we will not be asked to use this formula. We will rely on R outputs. So these quantities will be given to you using the R outputs. To get the estimated coefficients, you will learn them how to compute it in the lab. And those R outputs will be directly given to you in exam. So in between, let me highlight this yellow step and this yellow step. There is a big mathematics in between the two. That mathematics is, just for those who are interested, we take this model which is written in the scalar form. We take this model to the vector notation. By taking this model to the vector notation becomes y vector equals x beta plus epsilon. X is a matrix, beta is a vector, epsilon is a vector. And then we solve for this beta vector, and the solution for this beta vector comes out to be this x transpose x whole inverse x transpose y. We find it, we plug it into the model, and then write the model back into the scalar notation. But that whole thing is missing. You don't need to care about that one. So what you need to care about is the R output will be given to you, and these coefficients will be available in that output. You just need to interpret these coefficients. So we'll talk about the interpretation. But somewhere in the background, what will be working? Again, least square estimation will be working in the background. After doing that, in chapter 11, we moved on to testing hypothesis. When we moved on to testing hypothesis, because there was only one feature, we only tested about that one feature. Here you have K features. So here you will have 3 types of hypothesis, not only one type of hypothesis. You will have 3 types of hypothesis. One of the hypotheses will be that all the slopes are 0. What will this indicate? What will this indicate if all the betas are 0? That your whole model is insignificant, useless model. So one might be interested in testing the significance of full model. This will be tested again the way we tested in chapter 11 using F-test. That F-test will be SSR. There we divided it by 1 because there was one predictor. Here we will divide it by K because there are how many predictors? K predictors. There we subtracted n minus 2. There it was n minus 2. Why there was a 2? Number of features and the intercept. One feature, one intercept. How many features here? K and one intercept. So this will be K plus 1. So you will subtract n minus K minus 1. Again, go back to chapter 11. If K is 1, it will become again n minus 2, right? Go back to chapter 11. This is testing the significance of the full model. If somebody interested in testing the significance of the whole regression, you might be interested in testing the significance of a single feature. Now you remember I said in chapter 11, these two are the same things, because in chapter 11, there was only one beta 1, only one slope. So testing single slope or all slopes was the same thing. That's why you got the same decision there. Now they are different. The first case is where you are testing all slopes are 0. In the second case, you are testing that any one slope is 0. Let me not use J. I will use any specific value. Let's say beta 3 is 0. Against beta 3 is not equal to 0. So now you are testing whether x3 is significant or not in the regression. Is it significantly affecting y or not? X3, which has a coefficient beta 3. For this one, you will have a t-test. This will be beta 3 hat minus beta 3 naught, which is 0, divided by the standard error of beta 3 hat. Again, you don't need to know the expression of this standard error, because our output will be given to you. In that output, this standard error will be given to you. Okay, you just have to plug it into the T structure and go for either ejection region approach or p-value approach, whatever approach. The new thing in this chapter is the third case. What is the third case? I might be interested in testing the significance of whole model, or I might be testing the significance of only one predictor, or again, none of them, some of them. So I might be interested in all of them, one of them, or some of them. For example, beta 4 and beta 7 are 0 against H1, that at least one of them is not 0. Either beta 4 is not 0, or beta 7 is not 0, or both are not 0. For this one, we have a partial F test, not full F test. We call it partial F test. And this will be SSR of the bigger model minus SSR of the smaller model. Over R divided by MSE of the bigger model. And I will explain what is bigger model, what is smaller model, and all that. I will explain that one. This is the only new and different thing that we will see in chapter, which was in chapter 11. Everything else was covered in chapter 11, and we will cover with the same spirit in chapter 12. Exactly the same spirit. This is the only, let me highlight this one. This is the only new thing so far. There are two more new things, but this is the first one. There will be total 3 new things. Okay. Then in chapter 11, you estimated sigma square using MSE. Again, here, sigma hat square will be MSE. But this time, MSE will be SSE divided by n minus not 2, n minus k minus 1. Okay. What did you do again there? Again, there will be a shortcut method, or you can use this equation to get the SSE from shortcut method or the full method. Again, this testing for the whole regression is already covered up there, right? Then what did you do? Uses of regression. You will do uses of regression. Again, there will be 2 uses. One for the mean of y when x vector equals something. Number of study hours is 7 hours. IQ is 131. You fix the values for fixed values. So I'll call, instead of x, I'll call it X vector now. Many X's will be fixed, or why not? Again, this one will be called confidence interval. This one will be called prediction interval. Again, the formulas and computation is not with you. R output will be given to you. You just have to extract these from the R output and interpret them. So if I give you the R output and give you the two intervals, the wider one will be for prediction or confidence. Prediction will be wider, confidence will be narrower. Confidence is for the average, that will be narrower. Again, the same thing. Even with less intensity, there we were asking you to compute. Here we are not asking you to compute. We'll give you in terms of R outputs. You just have to take them from the output, interpret them. Okay. Goodness of fit. You talked about R square. We'll talk about R square again. It will be SSR over SST. But R square in multiple regression, it has a problem. What is the problem? If you keep adding the new predictors in the regression, keep adding new predictor, R square will keep going up. It never comes down. Even if you add a useless predictor. For example, you're trying to predict major 2 score. Okay. And one of the features is that whether the name of your instructor starts with A or not. Useless predictor. Even if you insert a useless predictor into the regression, R square will not come down. It will keep going up, which is a drawback of R square. And because of this drawback, statisticians, they think of adjusting this measure. And the adjusted version is called R square adjusted. That is equal to, this one is equal to 1 minus SSE over SST. That one is equal to 1 minus SSE over its degree of freedom divided by SST over its degree of freedom. So they just divided the both measures by their degree of freedom and they called it R square adjusted. Again, the formula for this R square adjusted is given in the formula sheet, but this R square adjusted will be provided in the R outputs. So this is the second new thing that we did not cover in chapter 11. And the third new thing that we will cover in chapter 12 is for all regressions, whether simple or multiple, it's that we did not talk about in chapter 11 was the assumptions of. Do you talk about assumptions in 291? Linearity, independence, equal variance, normality? No, I don't think. So this is what we will talk about, that for any linear regression, there are 4 assumptions. There are 4 assumptions. Number 1 assumption is that the relationship between y and x's is linear. The second assumption is that each data row is independent of other data rows. The third assumption is that the errors are normally distributed. The fourth assumption is that the errors have equal variance. And sometimes they do test for these assumptions. And if you want to remember that what are the 4 assumptions, look at the starts which I use red color for. Remember the line, but in exam, if you write line, they will give you 0. So remember the line, but remember what L stands for, what I stands for, what N stands for, and what E stands for. Okay. In this chapter, we will try to study some techniques if these assumptions are okay or not, using some plots. Again, the plots will be given to you from the R output. You just have to interpret those plots and see if the assumptions are okay in those plots or not. And that will be it. This is chapter 12. So all in all, in chapter 12, we will cover 3 new things that we did not cover in chapter 11. Number 1, we will cover partial F test, testing the portion of regression. Number 2, we covered R square adjusted. It's an adjusted version of R square. And number 3, we did not talk about the assumptions of regression. These assumptions of regression, they are applicable on simple and multiple both. Because of the highlighting, I think that red color disappear. So I will remove the highlighting. Let me highlight only like this. So the blue highlighted part is the new thing. And there are only 3 of them. Now let us go to the slides and start the chapter. Let's read through. It says that the simple linear regression model, it describes the relationship between a single predictor X and the response variable Y by this equation, which is yi equals beta naught plus beta 1 xi plus epsilon. Right? While this model, it captures the effect of one explanatory variable, a predictor, we call it predictor or feature, but real world phenomena are often influenced by several factors. Usually in real life, Y is affected by many predictors, many features. For example, the exam scores of a student, they depend not only on the hours studied, but also they depend upon the attendance, the prior knowledge of the course, the stress level, number of credit hours you are taking in this semester, your IQ, and many other things. So ignoring these additional variables, they can give you biased results, bad results. To address this, we extend the simple linear regression to include multiple predictors in a single model. And that single multiple linear regression model, where we allow for the k predictors denoted by x1, x2, all the way up to xk, this model is written as this one. Again, in this model, the total variation in y will be measured by SST. The variation which is explained by your regression will be measured by SSR, and the variation which is not explained by your model will be measured by SSE. Later, when we develop F-test and all that, you will see this equation again, where SST will be equal to SSR plus SSE. The difference here is you don't need expressions for these. They will be given to you in the output. They might give you a question where 2 of these are available and they ask you for the third one. Like we give you SST and SSR and ask for the sum of MSE. So MSE is basically SSE over n minus 2. So from this equation, you get SSE divided by n minus not 2, n minus k minus 1 this time. The interpretation will change a little bit. Because you added more features, the interpretation will change. What is the interpretation? What was the interpretation of beta 1 before? Before, you interpreted in chapter 11 that beta 1 is the average change in y due to a unit change in x1, right? Now you will say it is the average change in y due to a unit change in x1, comma, keeping the other predictors fixed. You cannot interpret the coefficient of x1 by leaving the others random. You have to fix the other ones and then interpret one. So you will add this statement for all the slopes. Which statement? Holding the other predictors fixed. So when you are talking about beta 2, you will say it is the average change in y due to a unit change in x2, comma, holding the other predictors. When you're talking about beta k, this should be k. When you're talking about beta k, you will say it is the average change in y due to a unit change in xk, comma, holding the other predictors, and so on. The interpretation of beta naught will not change. It will again be the average value of y when all the features are 0. But you will interpret it only when 0 is in the domain. 0 for all the predictors is in the domain. If 0 for all the predictors is not in the domain, what will you say? It has no practical meaning. It has no interpretation. Let us take this illustrative example. Suppose we wish to predict the fuel efficiency, which is y, of the vehicles using two predictors. Two predictors is now multiple regression. One of the predictors is the weight of the vehicle. What do you think how the weight is related with the fuel efficiency? If weight is higher, fuel efficiency will be higher or lower? If the vehicle is heavy, what happens to the fuel efficiency? So when you fit the regression, before fitting the regression as a scientist, what is your expectation about the sign of beta 1 hat? You expect it to be negative. If it is positive, you will be concerned that it doesn't match the theory. If you have a data for which the sign of the coefficient of x1 comes out to be positive, you should be worried. You should be concerned that it doesn't match the theory. Theory says that this should be negative, which is negative in this example also. So there are signs coming from the theory also. You have to make sure that they match. What is the second feature? Engine displacement, and I have no idea engine displacement is related to the fuel efficiency. How is it? I have no idea what is engine displacement. But according to what we see, it is also impacting the fuel efficiency negatively, which means that if the engine displacement is higher, fuel efficiency goes down. So the regression model that you fit is something like this. yi equals beta naught plus beta 1 x1i plus beta 2 x2i plus epsilon I, where x1i is the weight of the vehicle and x2i is the engine displacement. This is the model that you want to fit. This is the unknown population regression model. Now you will use the least square estimation. You will put the data into the least square estimator. The data will be processed by the least square estimation, and the least square estimation will give you beta naught hat, beta 1 hat, and beta 2 hat, right? Again, in this chapter, we will not go into the calculation, how the least square estimation process the data. We will not go into that one. But the only thing is it will process it somehow and give you these point estimates. And for this example, those point estimates came out to be 30.2. This is beta naught hat. 0.05, this is beta 1 hat. And 0.003, this is beta 2 hat. How will you interpret these quantities? Look at the bottom of your screen. It says that the interpretation for beta 1 hat is each additional kilogram of vehicle weight is associated with an average decrease, not increase, decrease because of the minus sign of 0.005 in the mileage, comma, holding the other predictors. What are the other predictors? There is only one other predictor. Which one? So we say holding the engine displacement fixed. If you have more other predictors, you will not mention one by one, just say holding the other predictors. Okay. Similarly, each additional cc of engine displacement is associated with an average decrease of 0.003 in mileage, holding the other predictors. What about the intercept? About the intercept 30.2 is the predicted value of y when weight and displacement are 0. Can you have a car which has a 0 weight? So what will you say about this quantity 30.2? It has no meaning, no interpretation. So it has no meaning. Even without looking at the data, you can see that x1 equals 0 is not possible. I'm not sure about x2, how does the engine displacement is computed from engine, but you cannot have a vehicle with 0 weight. You cannot have a vehicle with 0 weight. So even looking at the description of the variable, you can say that in this example, beta naught hat will have no meaning. So we will continue from here on in the next class. In the next class, we will move on towards the interval estimation and the 3 types of hypothesis. Next class, I will cover the 3 types of hypothesis. What are the 3 types of hypothesis in this, let's say, example? What if I ask you to test that in this regression, engine displacement is significantly affecting the fuel efficiency? What am I asking you to test? Test the hypothesis that engine displacement is significantly affecting the fuel efficiency. Beta 2 equals 0 against beta 2 not equal to 0. Which test you can use for testing? T-test for single predictor. What if I ask you to test the significance of the whole regression? You can use F-test for testing the significance of whole regression. What if I ask you to test that a part of regression? Now, if I take a part of that regression, it will be one predictor, which again, you can test it using the T. So for elaborating part, I will bring another model with 3 predictors where I will be interested in 2 of them. So we'll cover these 3 cases in the next class. We'll talk about R square adjusted in the next class. And finally, we'll talk about the uses of this regression in the next class. Probably next 2 classes, I will finish chapter 12.